Hello guys, this is Exhaust here, and today we'll be continuing fluorine. Now, with that out of the way, let's get into it. It is a carbon atom with 6 protons and 8 neutrons. In nature, almost all the elements exist as a mixture of 2 or more isotopes. Fluorine has many isotopes, but unlike most other elements, only has one natural isotope, called fluorine-19. This isotope has 9 protons and 10 neutrons. 9 plus 10 equals 19. The atomic weight of an element is the average weight of all isotopes of the element, taking into consideration of how often each isotope occurs. On a periodic table, the atomic weight of an element is often a number with a decimal fraction. For example, the atomic weight of carbon is 12.011. The atomic weight of fluorine is 18.998,404, which is often rounded to 19. Fluorine and the periodic table. Unlike Mendelov's chart, the periodic table that we use today lists the elements in order of increasing atomic number. The number of protons arranged like this. Many trends or patterns can be seen. You can use these trends to help classify an element by seeing where an element is located on the periodic table. You can predict whether it is a metal, a non-metal, or a metalloid, a substance that has characteristics of both metal and non-metals. If you look at the periodic table, you'll notice that the elements are divided in a line known as the staircase line. Metals are found to the left of this line and non-metals to the right. Most of the elements bordering the line are metalloids. Fluorine is found to the right of the staircase line. This is where you expect to find it because fluorine is a non-metallic gas. By definition, a non-metal is an element that does not have the characteristics of metal. Metals are easy to recognize by their physical traits. Generally, metals are solids that can be polished to be made shiny. They also conduct electricity. Most metals have the ability to be hammered into shapes without breaking. This is called malleability. Metals are also usually ductile, which means they're able to be pulled into wires. Substances such as wood, glass, or plastic are classified as nonmetals. Unlike metals, nonmetals are not shiny. They do not conduct heat or electricity well. Nearly half of nonmetal elements are gases. Some are liquids or solids. However, unlike solid metals, solid non-metal elements are brittle and will crumble and break apart if you pulled on or hammered. Groups and periods. As you look across the periodic table from left to right, each row of elements is called a period. Elements are arranged in periods by their atomic number or number of protons they have in their nuclei. As you go across the table from left to right, the atomic number increases by 1 from one element to the next. Each period has been assigned from number 1 to 8. The period of an element is found and can help you understand how the electrons are arranged in the element. Generally, the number of electronic shells that surround the nucleus of an element corresponds to its period number. For instance, fluorine is in period 2, so it has 2 shells with electrons surrounding its nucleus. There are 2 electrons in fluorine's innermost electron shell and 7 in its outermost shell. And to read down the periodic table from top to bottom, each column of elements is called a group or family. Just as you might have similar characteristics to other members of your family, the elements in the given family have similar properties. An element's chemical behavior and how it acts is determined by its electrons, partially those in its outer shell. The electrons in an atom's outermost shell are called valence electrons. All the elements in a given group behave similarly because they all have the same number of electrons in their valence shells. Fluorine has up to the group VIIa elements. This is a traditional way to label the groups using Roman numerals and divide them into a minus applied chemistry, IUPAC. An international group of scientists who set standards in chemistry have officially adopted a different way to label the groups of the periodic table. The number of groups from left to right use ABRIC numerals from 1 to 18, using the IUPAC system. Fluorine's group VIIa, is known as a group 17. Some scientists use the IUPAC system, but most chemists in the United States prefer a more traditional system. Other elements found in the fluorine in group VIIa are chlorine, bromine, iodine, and acetine. All these elements have 7 electrons in the outermost electron shell. Together, they form a very special group of elements called the halogens. Fluorine and the halogens. The electrons surrounding the nucleus of an atom are arranged into shells. Strict rules determine how many electrons each of these shells is able to hold. For instance, a shell closest to a nucleus is able to hold 2 electrons, while the next shell out is able to hold 8. Elements are very stable when their outermost electron shells are full. The halogens each have 7 electrons in their outermost electron shells. Because their outermost shells can potentially hold 8 electrons, they are nearly full. To filter their chlorine, bromine, iodine, and acetine. To fill their outermost electron shells, the halogens each tend to accept 1 electron from other elements. Fluorine's atom with 9 electrons is the smallest of the halogens. Fluorine has 17 electrons, bromine has 35, iodine has 55 free, and acetine atom is the largest of the halogen with 85 electrons surrounding its nucleus. The word halogen or halogen comes from the Greek words halos, meaning salt, and genes, meaning born. The halogens are known as the salt formers because of the way they accept electrons from metals to form salts. The halogens are all nonmetals, which means they are not shiny, do not conduct electricity, are not ductile or malleable, aka being hammered by a hammer. Of the 5 elements in the halogen group, only fluorine, chlorine, bromine, and iodine are all found in biological molecules. The last and largest halogen, acetine, is radioactively unstable, though it's never found in nature. All of the halogens are very reactive. Chapter 3. The properties of fluorine. A2 elements have characteristic physical and chemical properties. These properties help scientists identify and classify them. The physical properties of an element are those that can be observed without changing the element's identity. Some examples of physical properties are an element's phase or physical state at room temperature. Properties are element's phase or physical state at room temperature, density, and freezing point. The chemical properties of an element describe the element's ability to undergo chemical change by combining with other elements. A chemical change converts one kind of matter into a new kind of matter. If an element undergoes chemical change easily, it is said to be very reactive. Fluorine phase at room temperature. At room temperature, 68 degrees Fahrenheit, 20 degrees Celsius, an element is found in one of three phases: solid, liquid, or gas. Knowing the phase or physical state of an element in the room temperature helps scientists to identify it. At room temperature, the halogens exist in all three phases. Fluorine is found in the gas phase at room temperature. At room temperature, chlorine is also a gas and it's a green in color. Bromine is a brown liquid at room temperature, while iodine and acetine are solids. Iodine is purple, but scientists do not know the color of acetine because it's extremely unstable. Scientists have only been able to artificially produce about 1 millionth of a gram of acetine. It's not surprising, therefore, but very little is known about acetine's properties. Gases such as fluorine do not have definite shapes or volumes. If a gas is put in a container, it will take the shape of that container. Gases differ from solids and liquids in that they are able to be compressed and are able to expand. A gas will fill in a container of almost any size and shape. If it's put in a large container, the gas will expand to fill it. A gas can also be compressed to fit in a smaller container. If not confined to a container, gases will disperse into space. Cooling fluorine. At normal room temperature, fluorine is always a gas. However, if it's cooled to a low enough temperature, fluorine will become a liquid or even a solid. For chlorine to condense or turn into a liquid, the temperature must reach a chilly negative 307 degrees Fahrenheit, negative 188 degrees Celsius. At this condensation point, also called a boiling point, fluorine turns from a pale yellow gas to a yellow liquid. For fluorine to reach its freezing point or melting point, the temperature at which it becomes solid, the temperature has to drop even further to 363 degrees Fahrenheit, negative 219 degrees Celsius. As a solid, fluorine is almost a colorless crystal. As you move down the group into a periodic table, the melting and boiling points of the halogens increase. Fluorine and chlorine have melting and boiling points that are below room temperature. This is why they are found as gases at room temperature. Bromine's boiling point is above room temperature, but its melting point is below room temperature. It is condensed but not frozen. Therefore, bromine is a liquid at room temperature. Iodine has a melting and boiling points that are higher than room temperature. For this reason, iodine is still a solid at room temperature. The density of fluorine. Density is another physical property of matter. Density is the amount of a substance contained with a specific volume. Each element has a unique density associated with it. Therefore, an element's density is useful in helping the scientists to identify it. Fluorine has a density of 0.001696 grams per cubic centimeter at room temperature. The densities of different gases are often compared to the density of air. If a gas has a lower density than air, it will float in air. In contrast, if a gas has a higher density in air, the gas will sink in air. The density of air is 0.001207 grams per cubic centimeter at room temperature. That will make fluorine about 1.4 times denser than air. Since fluorine is slightly heavier than air, it will gradually sink to the ground if it is released. A diatomic molecule. All the halogens except for acetine are known for forming stable diatomic molecules. The word diatomic means two atoms. Carl O. Christie. In 1986, Carl O. Christie, while working in a laboratory at Edwards Air Force Base in California, made an outstanding discovery. While he was preparing for a conference that will celebrate the 100th anniversary of the discovery of fluorine, he found a way to make fluorine using only chemicals, no electricity. Because of the large amount of energy it takes to separate fluorine from other elements, many scientists have long believed such a feat was impossible. The diamic fluorine molecule contains two fluorine atoms and is written as F2. In the same way, diatomic chlorine, bromine, and iodine molecules are written as Cl2, Br2, and L2, I2. Respectively, their ability to form diatomic molecules to make the halogens special. Because besides the halogens, only three other elements form diatomic molecules like these. They are hydrogen, H2, oxygen, O2, and nitrogen, N2. In a diatomic fluorine molecule, each fluorine atom shares a pair of electrons with the other atom. When two atoms share electrons in this way, the link they form is called a covalent bond. The diatomic fluorine molecule that results from the covalent bond is much more stable, less reactive than the individual fluorine atoms. The stability results because by sharing electrons, each atom will fill its outer electron shell. Fluorine gas can consist of a pair of fluorine atoms bonded together, forming a diatomic molecule. This type of model of a molecule is called the bowl and stick model. Two bowls represent the two fluorine atoms, while a stick represents a single bond that holds the atoms together. This man's shoulder and chest were burned in an accident when fluorine reacted to the water in the body's cell, forming hydrofluoric acid. Hydrofluoric acid has many industrial uses, including the etching of glass, rust removal, and metal cleaning, and the manufacturing of electronics. Fluorine's reactivity. Where all the halogens are reactive, fluorine is by far the most reactive member in the group. This means that it combines with other elements very readily. The key to fluorine reactivity is the way that it attracts electrons to itself more strongly than any other element. An element that attracts electrons is described as being electronegative. Because the atoms in fluorine and the other halogens need only one more electron in the atom shell to become stable. They attract electrons very strongly. The fluorine atom is the smallest of the halogens, which means that its atom shell, electron shell, is closer to its nucleus. It is these electrons in the outermost shell that react with other elements. Therefore, the electrons from other elements are pulled with more force toward the positive protons in the fluorine's nucleus. This makes fluorine more likely to react with or combine with other elements. Fluorine is so reactive that it combines with almost every other element. It even reacts with some of the most non-reactive elements, such as palladium and gold, Au. Fluorine is unusual because, unlike most elements, it even reacts with other members of its group, the halogens. Fluorine's extreme reactivity explains why it took so long for scientists to separate it from other elements. It kept reacting with the containers they tried to collect it in. Fluorine's reactivity also makes it dangerous to work with. When it reacts with other elements, it often does so violently in the presence of hydrogen. Fluorine burns violently, forming hydrogen fluoride, HF. This happens spontaneously. Not even a match or a spark is needed to make it burn. If breathed in by an accident, fluorine gas can burn the lungs and skin. This burning is caused by fluorine reacting with the water that's found in the body cells, forming a corrosive chemical called hydrofluoric acid, a solution of HF in water. And that's for today's video. Hope you guys enjoyed, and I'll see you guys again very, very soon. Later.